Hi, welcome back to physics. We've been working on circuit analysis. Today we're going to be moving on with what's called series circuits, which is a slightly more advanced version of what we've already done. So let's dive right in. First of all, what is a series circuit? The idea of a series circuit is that, in this case, there's multiple objects in the circuit, resistors, light bulbs, what have you, but everything in the circuit is in one line. In other words, there's only one path for the current to take. Those charges are going to move around one single loop around and around, meaning any place there's a break in the path, either if you flip a switch or if you cut the line somewhere, it stops all the current everywhere from flowing. There's only one way for it to go, so if you stop that, that's it. Here's an example of a circuit diagram showing a series circuit. We have here one battery along the bottom. You see those alternating short and long lines to represent the battery. There is a voltmeter around there measuring the total voltage, as well as an ammeter next to it measuring the total current. Across the top, we have three resistors labeled R1, R2, and R3. Each one comes equipped with a voltmeter to measure the voltage change across that resistor, so V1, V2, and V3 respectively. We're given that this is a 24-volt battery that's powering the circuit, and we've measured R1 to be 3 ohms, R2 is 6 ohms, and R3 is 9. So that's what that circuit diagram would look like. Let's see what this means about what's actually going to happen. So there's only one path, so the current anywhere is going to be the same as the current everywhere. In other words, there's one single flow of electrons that goes around all the way around the loop. No changes anywhere. Another piece that's important with series circuits is the way that resistance combines. We've done work with one single resistor in a circuit. Adding in more, as long as you're doing it in series, means that you just add the resistances. There's an equation for that. It's very fancy. You can see it here. RT, or the total resistance, is equal to the sum of R1 plus R2 plus R3 plus however many R's there are, however many objects there are in the circuit. Just add together all those resistors, and you get this sum total RT. So for this example we just looked at, RT comes from adding 3 ohms plus 6 ohms plus 9, giving a total resistance of 18 ohms for the whole circuit. Great. But what does that mean? Well, moving on, we can use Ohm's law here. Hopefully you remember Ohm's law, but if you don't, it looks like this. V equals I times R. In this case, we're going to apply Ohm's law to the entire circuit. So Vt is the total voltage in the circuit. It is the total current coming out of the battery. Rt is the total resistance. That's what we just found by adding resistors. So for this specific circuit, we've got 24 volts on the left for our total voltage. I we don't know yet, but we did add the resistors to find an 18 ohm resistance. So if we solve that algebraically, we get I equals 1.33 amps. That's what that ammeter is going to read across the bottom. But since we know this is a series circuit and the current won't change, that means that's also the current that's going to be passing through each object. In other words, every resistor in the circuit will carry the same current load of 1.33 amps. Knowing that, and knowing that the Vt is the total voltage or the power source, we see that each resistor, each item in the circuit, is going to use up some of that potential difference in order to move current or electrical charges through it. So we used Ohm's law a moment ago on the entire circuit taken as a whole, but let's narrow our focus down and say, okay, what's happening in each individual resistor? We can use V equals IR, again, only having N as a subscript, where the N is a number of whichever object we're looking at. For example, across R1, we'll use V1 and I1 to find the voltage and current, respectively, in that resistor. So V1 we don't know. I1, though, is 1.33 amps because it's that everywhere in the circuit. And then R1 is 3 ohms, that's a given. So V1 must be 4.0 volts. We can do that again, changing the n's from 1 to 2. Same equation has V2 equaling, again, 1.33 amps, since that doesn't change, multiplied by the 6 ohm resistance of R2. That tells me that V2 must be 8.0 volts. So there's a bigger potential drop across 2 than there was across 1. Third time around, same equation. V3 equals I3 times R3. 1.33 amps is still the current in V3, but this time the resistance is 9 ohms. So our V3, or our voltage change across the third resistor, is going to be 12.0 volts. Now that's good to know on its own, but a side benefit is that we can take those three voltages we just calculated, 4.0 volts for the first, 8.0 volts for the second, and 12.0 volts for the third, and add those together. The total sum of all those potential drops across the three resistors is equal to the total gain that the battery supplied to begin with. You started out by giving 24 volts of potential to the circuit, and each resistor took out some until it was all gone at the end. So the sum, 8 plus 4 plus 12 equals 24, will work every time when you're doing a series circuit. So we have now a series of relationships here for this kind of circuit. First of all, Ohm's law, V equals IR, is useful not only to look at a specific piece of the circuit, like a resistor in it, but also you can use it for the totals, for the sum total of the entire circuit together. We also learned today that the total current is equal to the current in the first resistor, which is equal to the current in the second resistor, which is equal to the current in the third resistor, and this is true for any number of things in a series circuit. The current is always the same everywhere. Remember that. The next piece we found out was that resistance is added. So we have a total resistance of the entire circuit taken as a whole. That's going to be equal to the sum of R1 plus R2 plus R3 plus D2, however many resistors you have, all added together. That combination gives you RT, or the circuit total resistance. And finally, we know that voltages add as well. The total voltage, or the potential difference supplied by the battery, is going to be equal to the sum of the potential drops across all the resistors in the circuit. In other words, Vt equals V1 plus V2 plus V3 plus ... however many you have of those. So those are your basic rules of thumb for how to operate with series circuits. We'll try out a few problems together and see if we can get that worked out. Thanks for listening today. I'll see you next time.